this is Leo and welcome to my channel. Today let's solve some more LeetCode problems. Today's problem is shortest path in a grid with obstacles elimination. So we were given a m by n integer matrix grid where each cell is either 0, which means empty, or 1, means obstacle. We can move up and down, left and right, and to an empty cell only within one step. So we were asked to return the minimum number of steps to walk from the upper left corner, which is 0, 0, to the lower right corner, m minus 1 and minus 1, given that you can eliminate at most k obstacles, which means we can walk all the way down here through all the empty cells, but we can also eliminate k obstacles to get a straight line here. Return the minimum steps to get to the lower right corner. Okay, so if it's not possible to find such a path, we'll return -1. Let's take a look at the example. I believe it is this example here, the graph. The traditional way without any elimination is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. But if we can eliminate this obstacle, we can go straight down here, 1, 2, 3, 4, 5, 6, which gives us a more optimal solution with 6, with only one flip. Okay, and for this one, we were only going to eliminate one obstacle, and if we start from here, whichever we eliminate, we cannot reach to the bottom right corner. So in this case, we should return -1. Okay, this looks like a traditional BFS problem, and just we need to record how many obstacles we have eliminated. And once we can eliminate this, we can reach to this point, and we can record the optimal path. I mean, the optimal distance from all three directions, all the other directions. So, what should we do? We should record the steps so far and put them into another grid with the optimal solutions. In here, like for this one, we can access it from here or from the downside. Okay, so if we go from here, from 0, 0 to 1, 0, the step is 1, and we've used one elimination, which is within this k boundary. And if we go here, 1, 2, 3, 4, 5, 6, we can also reach this point, but the solution here would be 7. So we record the most optimal solution here, which is 1. Okay, and then we do all the same to see if we can reach this point. Okay, so this looks like a traditional BFS. So I'm going to start just the BFS solution. Okay, so let's first record the dimensions of the grid. And for the BFS solution, we need a Q, which records the coordinate of each grid. And what are we going to put in here? We're going to add the starting point and the step in here. Okay, so it's going to be X, Y, and steps. All right. Also, we will have a visited array, visit matrix. I'm going to record it in integer, which is m by n, and we're going to fix it with integer max value because we're recording the minimum steps to get here, right? So for int v visited arrays dot fill v versus integer max value. Okay, sounds good. And we have to initialize the first grid, which is 0, 0 is 0. Okay, because we don't have to do anything to get here. So now, while the queue is empty, while it's not empty, we have to make sure that there are multiple paths leading to one grid. Like if for this one, if there's only one way, we'll just go down here. Okay, but since we have other options here, we can start eliminating this obstacle. So we have to record its size, size, and when we have more than one points here, more than one path. Okay, sorry for the mistake. So we can pull it out. And now we have this. We're going to traverse its neighbors, right? So if it is the if it reaches to the bottom right corner, we can just return. Oh, sorry, here I have to initialize a distance for our return. And yeah, that's for the return. All right, next, for all the neighbors, int matrix, okay, I'm going to record them here, right? So this is going to be x plus 1 y, x minus 1 y, x y plus 1, x y minus 1. Okay, so for all the neighbors, let's see if we want to expand it to our neighbors. So there will be some scenarios that we don't want to explore. For example, first, if it's out of bound, continue. Okay, so if nx is less than 0, or ny is less than 0, or nx is larger than or equal to m, or ny is larger than or equal to n, continue. Okay, and second, if it's inbound and the elimination we're allowed to use exceeds this k. Okay, so out of eliminations, continue. Okay, so we have to record this. New k. Okay, I'm going to call it nk. Nk equals visited. No, equals the steps we've taken so far. Maybe let's call it eliminations. Okay, so the eliminations so far plus grid and x and y, because if it's empty, we're not going to eliminate anything, it remains the same. But if it's an obstacle, the elimination increment by 1, and we got a new nk. Okay, so if nk is larger than k, we're going to continue. Okay, also there's a third possibility. Once we're here, we have to update the visited matrix, right? But when do we update the visited matrix? That's because we have the most optimal solution here. Okay, so if we have more optimal solutions, continue. Okay, so let's see if visited and x and y, if it's less than this new k, we'll continue. All right. So when everything is done, we're going to update our visited and x and y. We're going to update it with nk. Okay, and that means we can reach to this point within the given eliminations. So we have to add this to our queue. And x and y and nk. And then we'll start from here, okay, until we reach here. So at each step, each expansion, we have to update our distance traveled so far. So I'll have dist plus, and if we cannot find anything, we'll return -1. Right? Yeah, I think it passed. So what is the complexity analysis? So for time complexity, in the worst case, we're going to traverse all the grids here. So it's going to be mn. And for the space complexity, we have a integer matrix, which is m by n. And yeah, I think that's most probably it. So yeah, that's it. Thank you for watching, and I'll see you in our next video.